Hi, welcome back to the Alkene edition playlist in organic chemistry here. So in this video, this is going to be the first part of a two-video series on a reaction known as anti-dihydroxylation, a pretty typical reaction that you would use in organic chemistry. And what's the overall utility in a reaction like this? Well, suppose I have two carbons, say this one and this one, that are adjacent to one another. Well, suppose I wanted to add a hydroxyl group to each of those carbons, one to each. And suppose I wanted to add them such that one would be on a wedge and the other would be on a dash. Well, anti-dihydroxylation is how you would do this. So let's break down the name of this reaction, okay? What is, first of all, hydroxyl? This part right here. Hydroxyl refers to the fact that we're dealing with an OH group. So whenever you have a hydroxyl group, that is when you have some R group, carbon, bound to an OH. And certainly I have that right here and here, okay? Di just refers to the fact that there's obviously two of them I'm adding. I'm adding one hydroxyl group to each of these carbons. And the anti in the name right here refers to the fact that when I add these two hydroxyl groups, I'm going to add them on opposite sides of the double bond, which ultimately means this reaction can't occur as written. We'll go into that in just a minute. But when I add the two hydroxyl groups across the double bond, they should add on opposite sides of the sigma bond, okay? So if this is the sigma bond right here, right, notice that one of them is going on a wedge, the other one's going the opposite direction on a dash, and that's characteristic of an anti-addition of any kind, okay? This type of molecule right here, where I have two hydroxyl groups that are next to each other, this is called, and also when they're on opposite sides, this is called a trans diol. Okay, and the ol, remember, is the suffix for an alcohol or a hydroxyl group, and the di refers to the fact that there's two of them, so it's a diol. The trans, of course, refers to the fact that it came from an anti-addition, meaning that these are on opposite sides of the sigma bond that joins the two carbons. Therefore, it's a trans diol. If for whatever reason you had something like this, maybe you had two that were on opposite side, or the same side of that sigma bond, then this would actually be a cis diol. Whenever you do have an anti-addition such as this, you term the product a trans diol. Okay? So let's break down this reaction right here, okay, up here. We hopefully know from studying hydrocarbons that simple alkanes are extremely unreactive. They don't react with anything. So you're not going to be able to do this reaction directly. That's not going to happen. So the utility in being able to make an alkene, which is something we looked at previously, like this alkene right here, is that the alkene is a lot more reactive than the alkane, and so it's a lot easier to dihydroxylate an alkene to make something like this. Okay? Now, when you do an anti-dihydroxylation, this is one of the reactions that's going to have to happen in two steps. This first step, this is the first reagent. I've written MCPBA. We're going to go into what that is in just a minute. But suffice it to say for now, this is what we call a peroxy acid. Now, what's the function of a peroxy acid? Well, if you use any peroxy acid on an alkene, the product you get is just some epoxide. And if you're not familiar with what an epoxide is, we're also going to go into what that is. But in order to do the complete dihydroxylation, there's a requirement here that you generate an epoxide first. And that's why you see this written as step 1. Once you have the epoxide, you can move into step 2 where you hydrolyze it with acid, H3O+, and you end up getting the diol, the trans diol. So this first video in this set of 2, we're going to look at this first step right here in terms of how you generate the epoxide. In the second video, we're going to look at actually how you get the main product that you usually go for, which is the trans diol. Okay? So let's do a little bit of a study on some of these functional groups so we can get an idea what they are. Okay? This right here, this is a generic epoxide. Okay? So in the epoxide, notice I have one carbon right here, I have a second carbon right here, and then notice that there's an atom here happens to be oxygen that bridges the two carbons. So basically what an epoxide is, if you're just looking at it like this, the epoxide is a carbon, and they're both bound to an oxygen. This right here, I mean, you could have other hydrogens and R groups sticking off of these, but this is the functional unit of the epoxide right here. Notice that it is a three-membered ring. The fact that it's a three-membered ring can make it very, very unstable. And we'll talk about that in just a minute. But notice that because it is a three-membered ring, that it's also going to have a significant amount of what we call ring strain. So whenever you think of strain, if something's strained, it doesn't like to be like that. You think that it would like to get out of the strain, right? So that's exactly what epoxides tend to do. It makes them very reactive. Part of the reason you have this strain is because of what's referred to as angle strain. If you think back to our hydrocarbon study, remember that the most stable rings tended to be six-membered rings. And they're usually carbon, but they can have an oxygen in them too. Six-membered rings were most stable. Five-membered rings a little bit less stable. Seven-membered rings kind of the same way. But as you start to decrease the carbons, or atoms in general in the ring, down to 4 and then down to 3 in this case, you ultimately generate a very high energy, unstable functional group. And that's exactly what an epoxide is. Epoxides are very, very reactive. So just a few things here about potential energy stability and reactivity. Because of the ring and angle strain here in the epoxide, the angles are pretty far from 109.5 degrees, the energy is actually very high. And that's going to ultimately imply that the epoxide is actually lowly stable. It's very unstable. And also they're very reactive. They have high reactivity, which means if you put anything, most things, the other reactive things in the vicinity of an epoxide, they will react with each other. Okay. We're also going to look at later in other chapters and other studies that you can actually make epoxides even more reactive. We'll actually take a quick look at that here in just a few minutes. But hopefully that gives you a little bit of intuition on what an epoxide functional group is. Okay. The other thing we talked about was that peroxy acid. And the peroxy acid, remember, was how we generate the epoxide functional group. This is one way to do it. There's certainly other ways. This is the best way when you have an alkene. So this only works when you have an alkene. Now, for the peroxy acid, I want to first review some other functional groups first. One thing hopefully you are familiar with is something called a carboxylic acid. When you have a carboxylic acid, remember you have this R group right here. It could be any R group really. But then the main thing is you sort of have this type of functional group here. And the way I sort of try to teach people carboxylic acids is it's sort of like you have an OH group, like an alcohol, but it's coordinated here to a carbonyl. Right, here's the carbonyl right there. You have this OH kind of bound to the carbonyl. Okay, that's your carboxylic acid. Another one that you may not have seen, or you may have just seen it if you did alkene additions, is what's termed a peroxide. Okay, all a peroxide is just when you have two oxygen atoms that are singly bound to each other. Okay, the simplest peroxide, it's not an organic peroxide, but it's hydrogen peroxide. You've probably used this. If you get a cut, you put that hydrogen peroxide on the wound, and it kills bacteria. It's bactericidal. But the functional group here of interest is this oxygen-oxygen single bond right there. That is the peroxide. If you have two carbon groups right here, or at least one carbon group, they don't have to be both carbon, but in this case they're going to be both carbon, then this is what we call an organic peroxide. Okay, when you have at least one of these R groups being carbon. Okay, now think of it like this. Think of taking this oxygen-oxygen single bond and sort of replacing that with this OH. So now instead of being a simple carboxylic acid, you now have this OOH. And so this is the functional group that we're talking about right here. It's sort of a carboxylic acid, but it has an extra oxygen-oxygen single bond. And then, of course, you have this R group, which could be a number of things, and you term this a peroxy acid. Okay, so If you see something like this, it's a peroxy acid. Carboxylic acids are more common, certainly, especially in biochemistry when you get there. And carboxylic acids are very unreactive. They're pretty stable. They don't really do anything. But peroxy acids, because they have this oxygen-oxygen single bond, which is pretty high energy, that makes peroxy acids a lot more reactive to things. And we're going to use that to our advantage when we do reactions like this. These right here are two things you should be familiar with. These are the two most common peroxy acids that we can use in reactions like this. The first one is called peroxyacetic acid. If you were just looking at simple acetic acid, that's just a carboxylic acid. It looks like this. Again, once again, notice that instead of the peroxy group right here, you just have an OH that's coordinated to this carbonyl, and that gives you your carboxylic acid. So what we can do is just simply throw in that extra oxygen-oxygen single bond, and it becomes peroxyacetic acid, right? Certainly a more complicated molecule that still obviously bears the peroxy acid in it is called metachloroperoxybenzoic acid. Okay, the R group is going to be this whole thing over here, this aromatic ring with a chlorine attached, and this is abbreviated usually as MCPBA. Okay, now in general, whenever you see, you have your reactants, your arrow that goes to the products. If this is what we call an epoxidation reaction, that's some vocabulary for you. Anytime you have a reaction that produces an epoxide, you term it an epoxidation. Anytime you have one of those reactions, usually what people do is they just put MCPBA on that arrow as one of the steps, or it's the only step. The obvious reason why you do that is nobody really wants to write out a metachloroperoxybenzoic acid. So MCPBA is an abbreviation that you should get pretty familiar with pretty quickly because it's a very useful reaction, so you're going to use it a lot. You'll use it in later chapters as well in organic. And certainly with MCPBA, it's usually the most common one that you're going to use to do epoxidations. So anytime you see this, it should be a clue that you're going to do an epoxidation, assuming that you have an alkene here. That's in general what you use them for. So hopefully that gives you a little bit of understanding of what epoxides and peroxy acids are. Hopefully what we can do now is just go over the general reaction of these things. And what I'm going to do also in this video is I'm going to sort of give you a foolproof way of predicting the products. A lot of times what professors will have you do is they'll just give you a reagent, and they'll give you the reactant, and then they'll say predict what the products are. I'm going to give you sort of a foolproof way to figure out what those are, but let's just go over the general reaction of epoxidation. All right, so here I have my alkene right here. Now here's the double bond right here. Ultimately, these are the pi electrons right there. The pi electrons are actually what are reactive here, and you notice in the final products, the pi electrons are actually gone, but the sigma bond remains. Okay, so when I use this peroxy acid right here, I could have written MCPBA, but I just have a generic peroxy acid. When I use that, the double bond is going to be gone. Okay, and essentially I'm going to draw an epoxide. Okay. That's going to be on one side of where that double bond was. Okay, notice here what I mean by that is I put the epoxide on wedges here, and then I put the other one on dashes here. So that probably means you know it's coming. There's going to be some stereochemical implications you're going to have to deal with, and that makes it kind of difficult. What I'm going to show you in a few minutes is kind of a foolproof way to go about predicting the products. But this is just to give you a general idea of the reactions. Okay. Notice in this one right here, there is a double bond. We obviously have that. But I also have a carbon that's already chiral. Okay. In this molecule right here, there are no chiral carbons. There aren't here in this third one either. But here there's a chiral carbon there. So if I treat it with, say, MCPBA or a generic peroxy acid, once again, I'm going to look at this pi bond right here. I'm going to remove that and essentially draw in here the epoxide. I'm going to put either the epoxide on dashes, I'm going to put it on wedges. Notice that this configuration right here of this carbon didn't change, right? There's nothing to change here because the reaction didn't take place on that carbon. The reaction only takes place on these two carbons right there that are part of the double bond, okay? So MCPBA doesn't act on anything else, so this should remain the same right here with that methyl group. Now, because this was already chiral, And now we've also generated 2 new chiral centers. Because there's already a chiral carbon, we're actually going to generate, in this case, a pair of diastereomers. So these are 2 stereoisomers, but they're diastereomeric to one another. Okay, that's because we already have a chiral carbon present. This is a case down here on the third one where we don't have a chiral carbon present, but we're going to apply the same logic. We have a double bond right here. That's the pi bond right there, the 2 pi electrons. I'm going to treat it with a peroxy acid. And notice what's going to happen. In terms of the epoxide, all I'm going to do is I'm going to put the epoxide here on dashes, put the epoxide here on wedges. Now, in this case, notice that on this double bond, this one actually had more than one substituent. Okay, when you have more than one substituent there, that's going to be a good indication that you're going to generate a chiral carbon. And notice here, this carbon right here actually is chiral. Okay, it's chiral in both cases. Okay, now that's the only chiral center, so these are enantiomeric to one another. These are enantiomeric to one another, enantiomers. But notice, how did I know? How did I know, say, to keep this ethyl group, in the plane, right? This sigma bond is still in the plane, right? This whole system is in the plane. How did I know to do that and say put this methyl group on a wedge and the epoxides on a dash? Here I have this structure where the epoxides on wedges, this methyl group is on a dash. How did I know to do all of that? Well, it turns out there is a method you can use that I found when I teach this. It works pretty well, and I'm going to show you that method right now. What we're going to do right now is actually practice predicting some of the products. So I'm going to make up some here. Okay, so let's look at, say, this compound right there. Let's look at that. Okay, and I want to treat it with peroxy acid, MCPBA, and drink when I predict the products. So here's what I'm going to do. Now I'm going to remember here that when I draw these molecules, remember hydrogens aren't indicated. However, it may help to actually indicate the hydrogens if they're not already shown. Okay, so we have that. Here's what I'm going to do. I'm going to take the double bond, and I did this in a different color, and I'm just going to simply draw a horizontal dotted line through it. Okay, that's all I'm going to do. The reason I'm going to do this is because I'm going to pick one side or the other. Say, for instance, I pick the top. Okay. I'm going to pick everything above that dotted line, every group, and so that what that includes is this group right here, which is a methyl, this group, which is an ethyl. I'm going to pick all of those, and they're going to remain the same. So all I'm going to do is I'm going to come over here and just redraw them. Okay, that's all I'm going to do. Okay. Then what I'm going to do, okay, is I'm going to remember that I'm essentially forming an epoxide. So then I'm just going to pick the epoxide, say in this case to be on a dash, right? Okay, I'm going to pick that to be on a dash, which means that whatever it was, do this in a different color, whatever it was below that dotted line goes on the other thing. So if this was on dashes, then this hydrogen has to be on a wedge, just like that one. Okay. Now you could say you could also form the other product. Okay. I'm going to do the same thing. So remember, everything above that dotted line remains the same. Okay. Now instead, I'm going to choose to put the epoxide on a wedge. Okay. Which means that when I add in the other functional groups down here, I have to force them to be on the opposite, which means this has to be on a dash, and so does that. And that's in general how I'm going to pick the products of these epoxidations. Okay? All right, let's do another example. So let's look at something like this. So put the double bond there. I'm actually going to change this up a little bit. Let's put a methyl group here. Okay? And now I want to treat this with peroxy acid, MCPBA, and I want to predict the products. Well, I'm going to do the same thing I did before. Now, this dotted line, I said it was horizontal. The whole point is it just has to be parallel to the alkene, the double bond, like that. Okay, and once again, I'm going to pick everything on one side of this double bond to remain the same, meaning it's just in the plane, right? So I'm just going to pick everything up here to remain the same, and I'm just going to remind us that that's in the plane, okay, of the screen, basically. So let's go ahead and redraw everything now. So I'm going to have this, right? That's going to remain the same. Also, keep in mind there is a hydrogen right there. That may help. Okay. Now I'm going to actually draw the epoxide. Well, first I'm going to draw, I'll just draw one on a wedge for change first. And then remember these functional groups right here have to be the opposite. So then I'm going to draw this methyl group on a dash. And this hydrogen I can go ahead and draw on a dash, right? Now I can draw the other product that forms, okay? So again, everything on this side of that dotted line I can pick to remain the same. I've done that. And then I can draw the epoxide. Let me draw it on a dash this time, okay? That means that these functional groups, hydrogen, methyl, have to be on the opposite ones now. So they'll be on wedges, CH3, and then this is going to be the hydrogen on a wedge, okay? And that's your product of this epoxidation. So let's do one more, and hopefully this will make sense. And then we'll look at the mechanism of actually how this occurs, the last thing. Okay. All right. So let me pick something. So let's do something like this. So just some weird molecule, right? So let's do MCPBA. And you know, I could also do peroxyacetic acid, right? But most people just put MCPBA. It's usually a pretty easy acronym to remember once you've been dealing with it for a while, and it's just readily available, so you just use that. All right, so I'm going to do the same thing. Let me also remember that there's two hydrogens right here, right? I'm also going to do something, though, and this may help you. Let me just, and I'll show you why I'm going to do this in a minute. Let me pick this hydrogen. I'm going to do it in blue, just because I don't want these two hydrogens to actually get confused with one another. Okay, but here's the idea. I'm going to draw that dotted line right here through that double bond. Okay, and let's just pick everything on this side to remain the same. Okay, meaning I'm going to pick it to be in the plane of the screen, right? So then I'm just going to redraw that. So here's this, right? Now what do? I draw the epoxide. Okay, let's just do it on a dashes first, right? So that means now everything else, meaning this is a propyl, this is a hydrogen, they have to be going on what? You guessed it, a wedge. So that means I'm going to draw a wedge here, and there's my propyl. And then for this, remember that's on a wedge too. That's the blue hydrogen, right? And that would be the product of this reaction, or one of them at least. Keep in mind we did generate a chiral center here. There's no other chiral centers, so we're going to have an enantiomer that forms also. Okay. So then what we do now? Well, we picked everything over here to be the same. Okay. So let's do that. Now, instead of doing this on dashes, I'm going to pick the epoxide to go on wedges. Okay, so there's that, which means where does the propyl have to be? Wedge or a dash? Right, it has to be on a dash. Okay, something like that. And then I also have to have this blue hydrogen on a dash. Okay, and then these would be the two products there. Remember, these are basically, this is not a chiral center right here, but these are, they're enantiomers to one another. What about these? Well, there were no other chiral centers there, so these are also enantiomers, okay? And now in this one, notice we have a chiral center here. This is a chiral center here. These are also enantiomers. So one thing that's important about epoxidation, and then ultimately the full anti-dihydroxylation we'll see in another video, is very often that is, you form enantiomers and sometimes diastereomers. Okay, that's something to watch out for in a lot of these additional reactions. You can form a lot of enantiomers and diastereomers. Okay, so hopefully this seeing predict the products actually makes sense. There is one other thing I do want to show you, just in case you were wondering, because it could be a question. What if instead of picking everything here to the right as being in the plane, I had picked, say, everything over on that side to be in the plane? Well, the reality is it doesn't matter, okay? You can, if you draw this dotted line, assuming you draw it right through that double bond, it doesn't matter which one you pick to be in the plane, whether it's the left or the right. So for example, let's say we pick this side to be the same, okay, in the plane. So what I'm going to do is I'm just going to go ahead and redraw this, right? This is my blue hydrogen, okay? And then what I do is I draw the epoxide, right? Let me do that in white again. Let's just draw it on dashes first, right? Which means that this methyl right here has to be on what? A wedge, right? And then this hydrogen over here has to be on a wedge as well. Remember, I also am going to get the enantiomer. So put that hydrogen blue right there. That means I have to pick that epoxide to be on a wedge, right? And then my methyl would therefore be on a dash, and that hydrogen in white would be on a dash. Now, what you can show, and I challenge you to do this could be kind of some good practice for you, is you can rotate these to show, essentially, that these two molecules right here are exactly the same molecules as these two right here. Okay, they're exactly the same. So I can promise you, whichever side you pick to be the same, it actually doesn't matter, because ultimately, no matter what you do, you're going to get the same two molecules. Now they're probably going to look a little bit different. You're going to have to rotate them a little bit, but they are going to be the same molecules exactly. Okay, so hopefully that helps you a little bit. All right, so now what I want to do is actually two more things. I know I said one more thing. Let me do two more things. I'm going to show you the mechanism. It's not really super imperative that you know the mechanism, but it will show you it anyways, just in case it was to crop up. And then after that, I want to show you a few biological applications of this. I try to keep it a little biologically active and relevant in here because most people who are taking this class are probably going into something biologically related. Okay, so let me actually show you these mechanistic steps in green right here. So this is your peroxy acid. I've drawn it in a little bit of a different orientation, and then here's your alkene over here. So here's what's going to happen. These pi bonds in this carbonyl right here of the peroxy acid, they're essentially going to come out and try to take this proton right here from the peroxy acid. This is sort of like you could consider it, it's a proton transfer within the molecule itself. That's going to cause these electrons ultimately to attack this carbon right there. Okay, when they attack there, this pi bond right here will actually attack that oxygen. What that's going to do is it's going to force essentially loss of a leaving group, and then these pi electrons, or not pi electrons, excuse me, sigma electrons actually are going to come here and form a double bond there. So what you're ultimately left with is actually a carboxylic acid, right? And then you actually get the epoxide right here. So this is actually right here. This is just the transition state right here. What you can ultimately see is these two bonds right here. These are bonds that are forming, right? Ultimately, this oxygen is forming a bond with this hydrogen, but this bond right here, this is a bond that's breaking, and this is a bond that's breaking right here. And ultimately, this is going to give you the epoxide you want. Now, remember, the epoxide can form on either side, so in this case, you also could theoretically end up with this, right? But just remember that in some cases like this, those are the same molecule. Okay, I promise you, if you were to take this molecule right here, do what they call a pancake flip it over 180 degrees, you'll get this molecule. They're the same. So sometimes you don't get an enantiomer, sometimes you actually get the same molecule. This would be one case where that happens. Okay. Now, that's the mechanism of epoxidation. What I want to show you is some biological applications of this that hopefully you might find interesting. Okay. So this right here, carbamazepine, this is a drug, a psychiatric medication, and carbamazepine is used as an anticonvulsant. Some people will actually use it to treat bipolar disorder. Whether or not it works, I mean, that's subject to question, obviously. But anytime you take drugs, so psychiatric medications. It could be a beta blocker for the heart. It could be anything that these chemists made through synthesis and the doctors give you. Okay, these drugs are treated as foreign molecules. Okay, there's an enzyme in humans called, it's a class of enzymes that is, called cytochrome P450s. Cytochrome P450s, if you're not familiar with them, they're basically your drug detoxification system. So they're going to do reactions on different drugs, ultimately to help the kidneys and, well, mostly the kidneys to ultimately excrete them in the urine. Okay, they're going to do different transformations to them. There's one type of P450 reaction called an epoxidation reaction, and therefore this type of P450 is termed an epoxidase. ACE just refers to the fact that it's an enzyme and it's epoxidating, so it's an epoxidase. This is a reaction that occurs in the liver. If you have carbamazepine right here, there is a relatively reactive double bond right here. This is the double bond of question. And it turns out that double bond can actually be epoxidated. Now, obviously, when you're dealing in living systems, are you going to use MCPBA? No. Ultimately, there's going to be a different set of reagents, which include molecular oxygen. That's one of them. But there's going to be a different set of reagents that are going to be used to do these reactions. But epoxides actually, which is this functional group right there, epoxides are useful in the degradation of foreign molecules like drugs and medications, because remember, epoxides are reactive. So actually what's going to happen in another step through a different enzyme, that's also called epoxide hydrolase, it's going to actually form a transdiol, which was ultimately what we were trying to do with anti-dihydroxylation. It's just going to do it through a little bit of a different mechanism and different reagents. But this is one use for it. We take a double bond, an alkene, and we epoxidate it. And this is ultimately what we refer to as a drug metabolite. Okay. Another example is something like this. Now, there's an important note here. First of all, this molecule you should recognize as benzene. Okay. One thing I want to have you take notice of. If I have this reaction right here, so if I try to do benzene and do the simple organic lab reaction, MCPBA, there is no reaction here. Okay. Why is there no reaction? Well, when you're doing things in a lab, you're doing things in a beaker of some sort or something like that. You may be doing it under reflux, whatever. But benzene is what we call an aromatic compound. Now, we haven't done the study of aromaticity yet, but aromatic compounds are not just stable, they are exceptionally stable. And so a lot of the reactions that you can do on simple alkenes, if it's just a simple double bond like that, they don't work when you have aromatic compounds. There are some more complicated aromatic compounds. Sometimes you can have multiple ones connected to each other like this. And MCPBA will still not work on that. It won't work on that compound, and it certainly won't work on benzene. Okay, the simplest aromatic six-membered ring. So that won't work on those compounds. However, in biological systems, there are exceptions to these rules we have in organic. That's why enzymes are actually so amazing, is they can do things that you can't do in a lab. There's no way we can really do them effectively, and they can do them pretty much with 100% yield in living systems. Example, sometimes in some cases, for whatever reason, usually if you're working in some lab or you're around some kind of industrial occupation or something like that, you can ingest benzene. It's something you can inhale. It can get into your nasal mucosa where you actually have some of these enzymes. They're not just in the liver. Or maybe somehow benzene, you ingested a little bit of it. Okay. Well, it turns out that this P450 epoxidase can also handle benzene. Okay. So more or less what the enzyme is able to do is it's able to sort of treat this double bond, say for instance, as if it's completely isolated from these other two. Okay, and it's just going to do this epoxidation reaction sort of in the absence of these double bonds right there. Okay, and so this is an important note here, is that some enzymes, or enzymes in general, may violate some rules observed in regular organic chemistry. Can't emphasize that enough, but hopefully you're able to see some application of epoxides. And that's basically going to conclude this video. Hopefully you understand how to predict the products of these epoxidation reactions. In the next video, we're going to do our completion of this part and show you how anti-dihydroxylation works. See you in the next video. Hope that helped.